June 6, 1944. Royal Aircraft Establishment, Farnborough, England. Dr. Margaret Whitley carefully placed a fragment of twisted German steel under her electron microscope as Allied forces stormed the beaches of Normandy, just 200 miles away. The metal sample had been torn from a crashed Messerschmitt Tu-62 jet fighter, Hitler's revolutionary Wunderwaffe, that promised to turn the tide of World War II. But what Whitley saw through her microscope would shatter Nazi claims about German technological superiority and reveal that the Third Reich's most advanced weapons were fundamentally flawed at the molecular level. The laboratory was filled with fragments of German equipment that had been arriving at Farnborough for months, twisted pieces of tank armor from destroyed Panthers and Tigers, turbine blades from jet engines that had disintegrated during operation, artillery shell casings that had exploded in gun barrels, and submarine hull sections that had buckled under pressure far below their rated limits. Each piece told a story of catastrophic failure that contradicted German propaganda about superior engineering and advanced metallurgy. The Messerschmitt fragment in front of Whitley had come from an aircraft that crashed not due to enemy fire, but because its engine had literally torn itself apart during flight, sending metal fragments through the fuselage and killing the pilot instantly. The steel structure showed catastrophic crystal fractures that made the metal as brittle as glass under stress. Inclusions of sulfur and phosphorus riddled the alloy like hidden time bombs waiting to explode. The metallurgy was so poor that German superweapons were literally built to break, their impressive appearance masking internal weaknesses that would doom them to failure regardless of their revolutionary designs. Under high magnification, Whitley could see the telltale signs of manufacturing problems that would have been immediately obvious to any competent metallurgist. The grain boundaries were irregular and contaminated with impurities that created weak points throughout the steel matrix. Carbon distribution was so uneven that some areas were too soft to maintain structural integrity, while others were so hard they cracked under thermal expansion. The implications were staggering. If this level of metallurgical failure existed in Germany's most advanced weapons, then the entire Nazi war machine might be far more vulnerable than Allied intelligence had realized. The fearsome German military technology that had dominated European battlefields for years could be fundamentally flawed at the atomic level. This is the story of how British materials scientists exposed the fatal flaws in Nazi Germany's wonder weapons through meticulous analysis that revealed a stunning truth. Hitler's most advanced technologies were crippled by metallurgical failures that made them more dangerous to their operators than to Allied forces. But to understand why German steel was failing catastrophically, you must first understand how the Nazi war machine had systematically destroyed its own industrial capacity through ideology, slave labor, and the pursuit of quantity over quality that would ultimately seal Germany's defeat. By 1944, Nazi Germany appeared to possess technological capabilities that far exceeded those of the Allied nations. Jet aircraft roared through European skies at speeds no Allied fighter could match. V-2 rockets struck London with devastating force from launch sites hundreds of miles away. Tiger tanks dominated battlefields with armor so thick that Allied anti-tank weapons bounced off harmlessly. Submarine wolf packs prowled the Atlantic using advanced snorkel technology that allowed them to remain submerged for weeks. German propaganda proclaimed these wonder weapons as proof of Aryan technological superiority that would guarantee final victory despite temporary setbacks. Radio broadcasts promised that revolutionary German science would sweep Allied forces from the continent and establish the Thousand-Year Reich through technological dominance that no enemy could overcome. The Messerschmitt Tu-62 jet fighter represented the pinnacle of German aeronautical achievement, capable of speeds exceeding 500 miles per hour, that made it nearly impossible for Allied fighters to intercept. Its twin Junkers Jumo 004 turbojet engines produced over 3,800 pounds of combined thrust, propelling the aircraft faster than any operational Allied fighter. The Panzer VI Tiger tank weighed 57 tons and mounted an 88mm gun that could destroy any Allied tank at ranges exceeding 2 miles. Its frontal armor was 100 millimeters thick, making it virtually invulnerable to most Allied anti-tank weapons. Allied tank crews had learned to fear the distinctive sound of Tiger engines and the crack of their high-velocity guns. The V-2 rocket stood 46 feet tall and could carry a 1-ton warhead over distances exceeding 200 miles at speeds that made interception impossible. These weapons struck London without warning, their supersonic approach preventing any defensive measures. Each rocket represented technology decades ahead of anything the Allies possessed. Type Cadouas U-boats incorporated revolutionary hull designs that allowed underwater speeds exceeding 17 knots, faster than most Allied escort vessels could manage on the surface. Advanced battery systems enabled submerged operations for extended periods without the need to surface for air or battery charging. But Allied intelligence officers had begun noticing disturbing patterns in captured German equipment that contradicted the impressive specifications and propaganda claims. Jet engines that should have operated for hundreds of hours were failing after just 25 hours of use, forcing German pilots to treat each flight as potentially their last. Tank transmissions were breaking down with shocking frequency, leaving expensive armored vehicles stranded on battlefields where they became easy targets for Allied artillery. Artillery pieces were exploding during firing, killing their own crews more often than enemy soldiers. German gun crews had developed a superstition about ghost rounds that would detonate in the barrel without warning, turning sophisticated weapons into death traps for their operators. The fear was so widespread that some artillery units refused to use certain types of ammunition. V-2 rockets were failing at alarming rates, with approximately 20% exploding during launch or disintegrating during flight. The unreliability meant that German rocket forces were as dangerous to their own personnel as to Allied targets. Launch sites were littered with the wreckage of failed rockets that had exploded before leaving German territory. Tiger tanks were requiring constant maintenance that consumed enormous amounts of time and resources. Final drive failures were so common that German tank crews carried spare parts that weighed hundreds of pounds. Many Tigers were abandoned not due to combat damage, but because mechanical failures made them impossible to repair in field conditions. The Royal Aircraft Establishment at Farnborough had been tasked with analyzing captured German technology to understand both its capabilities and its limitations. What began as routine technical intelligence soon revealed systematic problems that suggested fundamental flaws in German manufacturing processes that extended far beyond individual weapon systems. Dr. Margaret Whitley led the metallurgical analysis team that would uncover the truth about German steel quality. Born September 15, 1912 in Sheffield, England, Whitley had grown up in the heart of Britain's steel industry, where her father worked as a metallurgical engineer for major steel producers. Her childhood had been spent among the blast furnaces and rolling mills that made Sheffield the steel capital of the world. Sheffield's steel industry had dominated world markets for over a century through innovations in alloy development and quality control that made British steel synonymous with reliability and strength. The city's steelmakers had developed techniques for controlling carbon content, eliminating impurities, and creating specialized alloys that could withstand extreme conditions without failure. Whitley had learned metallurgy from childhood, observing the careful processes that created steel capable of withstanding extreme stresses under demanding conditions. She understood that quality steel required precise control of temperature, chemistry, and cooling rates throughout every stage of production. Small variations in any of these factors could create catastrophic weaknesses that might not become apparent until components failed under stress. Her father had taught her to recognize the subtle signs of metallurgical problems that could doom steel components to premature failure. Grain structure, inclusion content, and chemical composition all had to be carefully controlled to produce steel that could perform reliably under combat conditions. The slightest deviation from proper procedures could create materials that appeared satisfactory, but contained hidden flaws. She completed her doctorate in materials science at Cambridge University in 1936, with a dissertation on fatigue failure mechanisms in high-stress steel components. Her research had focused on understanding how microscopic defects could propagate through steel structures until they caused catastrophic failures that appeared to occur without warning. Whitley joined the Royal Aircraft Establishment in 1939, just as war clouds were gathering over Europe. Her expertise in steel analysis and failure investigation made her invaluable for understanding why aircraft components failed under combat stress. The demanding conditions of aerial warfare created stresses that revealed weaknesses in materials that might perform adequately under normal circumstances. When German equipment began arriving at Farnborough for analysis, Whitley immediately noticed anomalies that suggested serious quality control problems. Steel samples showed inconsistent hardness, irregular grain structure, and inclusion levels that would have been rejected by any competent British manufacturer. The differences were so dramatic that she initially suspected the samples had been deliberately sabotaged. The first major breakthrough came from analysis of a Junkers Jumo 004 jet engine recovered from a crashed Messerschmitt 262. The engine represented the pinnacle of German technology, capable of producing over 1,900 pounds of thrust and propelling aircraft to speeds exceeding 500 miles per hour. German engineers had achieved unprecedented performance levels that Allied designers were struggling to match. But Whitley's examination revealed catastrophic metallurgical flaws throughout the engine's critical components that made such performance impossible to sustain. Turbine blades showed stress fractures that originated from sulfur inclusions in the steel matrix, creating weakness patterns that would inevitably lead to blade separation during high-speed operation. The sulfur inclusions appeared as dark streaks under microscopic examination, indicating that German steelmakers were using ores with impurity levels that would have been unacceptable to British manufacturers. Sulfur content exceeded acceptable limits by factors of 10 or more, creating materials that were fundamentally unsuitable for high-stress applications. Bearing races had been manufactured from steel, with carbon content so inconsistent that some areas were too soft to maintain proper tolerances, while others were so hard they cracked under thermal stress. The variation in hardness created uneven wear patterns that would cause bearings to fail within hours of operation rather than the hundreds of hours required for practical use. Carbon distribution analysis revealed that German heat treatment processes were not achieving the uniform temperature control necessary for proper steel hardening. Some areas of components had been heated to proper temperatures, while adjacent areas remained too cool for adequate heat treatment. The resulting material properties varied dramatically within individual components. The compressor housing exhibited what metallurgists call orange peel texture, indicating that the steel had been worked at improper temperatures during manufacturing. This created internal stresses that would inevitably lead to catastrophic failure once the engine reached operating temperatures and rotational speeds. The forging process had introduced defects rather than eliminating them. Microscopic examination revealed that German forging operations were being conducted at temperatures too low for proper metal flow. Instead of creating strong, uniform grain structures, the forging process was creating areas of weakness where metal flow had been interrupted by improper temperature control. Most shocking was the discovery that German engineers appeared to be aware of these problems, but had been forced to proceed with production using defective materials. Engineering notes found with captured equipment revealed desperate attempts to compensate for poor steel quality through design modifications that reduced performance and reliability. Internal German documents captured with the engine showed that test facilities had recommended rejection of the steel batches used in production, but military procurement officers had overruled these recommendations due to urgent delivery schedules. Quality control personnel had been ordered to accept materials that they knew were substandard. Whitley's team expanded their analysis to include samples from every major German weapons system captured by Allied forces: Tiger tank armor plates, V-2 rocket components, submarine hull sections, aircraft engine parts, and artillery gun tubes all underwent comprehensive metallurgical examination, using the most advanced analytical techniques available. Tiger tank armor samples revealed particular problems with weld quality that made these formidable weapons vulnerable to failure at their strongest points. Welded joints that should have been stronger than the base metal were actually weaker due to improper welding procedures and contaminated filler materials. X-ray analysis of weld sections showed extensive porosity and inclusion contamination that created weak points throughout the armor structure. German welders were using techniques that introduced air bubbles and foreign materials into critical joints, creating failure points that enemy fire could exploit more easily than solid armor plate. V-2 rocket engine components exhibited severe corrosion damage that indicated German metallurgists had lost control of alloy composition. Components that should have resisted oxidation were showing rust formation that would have been impossible with properly formulated stainless steels. Chemical analysis revealed that critical alloying elements like chromium and nickel were present in concentrations far below specification levels. German steelmakers were apparently substituting inferior materials due to shortages of strategic metals, creating alloys that could not perform their intended functions. Submarine hull sections showed stress cracking patterns that indicated fundamental problems with steel composition and heat treatment. The cracks followed grain boundaries, suggesting that German heat treatment processes were creating weak areas rather than strengthening the materials. The results were consistent across all German weapon systems. Steel quality had deteriorated dramatically since 1942, with problems becoming increasingly severe as the war progressed. What had begun as isolated quality control issues had evolved into systematic metallurgical failures that affected every aspect of German weapons production. The root causes of German steel failures traced back to decisions made at the highest levels of Nazi leadership. Adolf Hitler's ideology had systematically undermined German industrial capacity through policies that prioritized political loyalty over technical competence and quantity over quality in ways that proved catastrophically counterproductive. The Nazi regime had purged Jewish scientists and engineers from German industry, eliminating decades of accumulated expertise in metallurgy and materials science. Many of Germany's most experienced steel experts had fled to Britain and America, taking their knowledge with them and leaving German industry dependent on less experienced personnel who lacked the deep understanding necessary for maintaining quality standards. Dr. Fritz Haber, who had developed the Haber-Bosch process for ammonia synthesis that enabled German explosives production, had been forced to flee Germany in 1933. Dr. Gustav Hertz, a Nobel Prize winner in physics whose work on electron bombardment had applications in materials testing, had emigrated to the Soviet Union. Hundreds of other leading scientists had abandoned German research institutions. The exodus of technical expertise created knowledge gaps that could not be filled quickly through normal training programs. Metallurgy required years of experience to master, with subtle understanding of how different variables affected final product quality. The replacement of experienced personnel with politically reliable but technically inexperienced workers created conditions for systematic quality failures. Slave labor had replaced skilled German workers in critical manufacturing roles throughout the steel industry. Prisoners of war, concentration camp inmates, and foreign workers were forced to operate complex steelmaking equipment without proper training or motivation to produce quality products. The psychological conditions under which they worked made sabotage inevitable. Sabotage was common and often subtle, with acts of resistance that degraded product quality without being immediately detectable. Foreign workers would adjust furnace temperatures slightly, creating improper heat treatment conditions. They would introduce contaminants into steel batches or modify cooling procedures in ways that weakened final products without causing obvious immediate failures. The scale of sabotage was documented in captured German security reports that described thousands of incidents where production equipment had been damaged or operating procedures had been deliberately altered. Security personnel estimated that sabotage was reducing German steel quality significantly compared to pre-war standards. Raw material shortages forced German steelmakers to use inferior ores and recycled materials that contained impurities impossible to remove with available technology. Critical alloying elements like chromium, nickel, and molybdenum became increasingly scarce as Allied bombing disrupted supply lines and naval blockades prevented imports from neutral countries. Swedish iron ore, which had been the foundation of German steel quality before the war, became increasingly difficult to obtain as Allied naval forces disrupted shipping routes through the Baltic Sea. German steelmakers were forced to use domestic ores with higher sulfur and phosphorus content that created inherent quality problems. Recycled steel from damaged equipment and captured Allied material introduced unknown contaminants into German steel production. Scrap metal often contained alloys and treatments that were incompatible with German manufacturing processes, creating unpredictable material properties in finished products. The German war economy's emphasis on maximum production quotas created incentives for managers to ship substandard products rather than take time for proper quality control. Inspection procedures were abbreviated or eliminated entirely to meet impossible delivery schedules imposed by military planners who prioritized quantity over reliability. Factory managers faced execution for failing to meet production targets, creating powerful incentives to ship products regardless of quality. Quality control inspectors were pressured to approve materials that they knew were defective, with rejection rates artificially reduced through administrative pressure. Temperature control in German steel furnaces became increasingly erratic, as coal quality deteriorated and electrical power became unreliable due to bombing damage. Proper heat treatment required precise temperature control that German industry could no longer maintain consistently across its production facilities. Power outages during critical manufacturing stages ruined entire batches of steel components. Whitley's analysis revealed specific failure mechanisms that explained why German weapons performed poorly despite their impressive specifications. Steel components that looked adequate during initial testing failed rapidly under operational stress due to metallurgical flaws that could only be detected through sophisticated analysis. Fatigue failures were endemic in German equipment due to inclusions and grain boundary weaknesses that created stress concentrations under cyclic loading. Components that should have lasted thousands of hours failed after hundreds of hours when subjected to the repeated stresses of combat operations. Corrosion resistance had been compromised by poor alloy composition and inadequate surface treatments. German equipment deployed to harsh environments like the Russian front or North African desert experienced accelerated deterioration that rendered weapons systems unreliable within months of deployment. Thermal shock resistance was particularly poor in German steel alloys, causing failures when components experienced rapid temperature changes. Jet engines, artillery pieces, and tank transmissions all suffered catastrophic failures when thermal gradients exceeded the steel's ability to accommodate expansion and contraction. The implications of Whitley's findings extended far beyond technical curiosity. German weapons that appeared formidable on paper were actually vulnerable to failure at critical moments. Allied forces could exploit these weaknesses through tactics that imposed maximum stress on German equipment. Tank crews learned to target German tank transmissions, which were known to fail under sustained high-speed operation. Artillery units concentrated fire on German gun positions, knowing that enemy weapons had high failure rates that would eliminate threats even without direct hits. Aircraft maintenance crews understood that captured German jet engines could not be operated at full power for extended periods without catastrophic failure. This knowledge influenced tactical planning and resource allocation throughout Allied air operations. The intelligence value of Whitley's work extended to post-war reconstruction planning. Allied leaders realized that German industrial capacity had been more severely damaged than previously understood, affecting estimates of how long rebuilding would require and what technologies Germany might be able to develop independently. Manufacturing quality problems were not limited to weapons systems. Analysis of captured German industrial equipment revealed similar metallurgical failures in civilian machinery, transportation systems, and infrastructure components. The deterioration of German steel quality affected every aspect of the Nazi war economy. Railroad equipment showed particularly severe quality problems that explained the increasing frequency of transportation breakdowns that disrupted German logistics. Locomotive wheels, axles, and track components were failing at rates that made reliable transportation increasingly difficult to maintain. Chemical plant equipment captured in Germany exhibited corrosion and stress cracking that had reduced production capacity and created safety hazards for workers. Poor steel quality contributed to industrial accidents that killed experienced personnel and damaged irreplaceable production facilities. Power generation equipment showed metal fatigue and thermal damage that reduced electrical output and created cascade failures throughout German industrial systems. Poor metallurgy had created vulnerabilities that Allied bombing campaigns exploited to maximum effect. Whitley's team developed detailed technical reports that were distributed throughout Allied intelligence services and shared with American and Soviet analysts. The information influenced everything from tactical battlefield decisions to strategic bombing target selection. American metallurgists confirmed Whitley's findings through independent analysis of German equipment captured on the Western Front. Soviet technical intelligence teams reported similar observations from equipment captured during their advance through Eastern Europe. The consistency of metallurgical failures across all German weapons systems indicated that the problems were systematic rather than isolated, suggesting that German industrial capacity had been fundamentally compromised by policies and resource constraints that could not be quickly corrected. Post-war investigations revealed the full extent of German steel quality deterioration. German engineering reports captured after the surrender documented systematic attempts to compensate for metallurgical failures through design changes that reduced performance and increased complexity. German test facilities contained hundreds of failed components that had been removed from service due to premature failure. Maintenance records showed that German equipment required far more frequent repairs and replacement than comparable Allied systems. Production statistics revealed that German factories were producing millions of defective components that failed quality control inspections but were shipped anyway due to desperate military needs. The waste of raw materials and manufacturing capacity represented a massive misallocation of resources that contributed to German defeat. The human cost of metallurgical failures was documented in German military medical records that showed increasing numbers of casualties caused by equipment failures rather than enemy action. Tank crews killed by transmission explosions, air crew deaths from engine failures, and artillery crews killed by gun tube ruptures all reflected the deadly consequences of poor steel quality. Whitley's work continued after the war as part of British efforts to understand German technological capabilities and prevent the transfer of dangerous technologies to other nations. Her analysis helped shape Allied policies toward German scientists and industrial facilities during the occupation period. The metallurgical intelligence gathered by Whitley's team influenced the development of improved Allied steel production techniques and quality control procedures. Understanding German failures helped British and American industry avoid similar problems in their own weapons development programs. Modern materials science owes significant debt to the analytical techniques developed during World War II for evaluating captured enemy equipment. Electron microscopy, X-ray crystallography, and chemical analysis methods pioneered for intelligence purposes became standard tools for industrial quality control. The lessons learned from German metallurgical failures influenced post-war industrial development throughout the Western world. Quality control systems, worker training programs, and management structures were designed to prevent the systematic degradation that had crippled German war production. Margaret Whitley continued her career in materials science, eventually becoming one of Britain's leading experts in metal fatigue and failure analysis. Her wartime work established principles that continue to guide materials testing and quality assurance in critical applications. The steel samples analyzed at Farnborough are now preserved in the Science Museum in London as examples of how metallurgical analysis contributed to Allied victory. The twisted fragments of German steel serve as reminders that technological superiority requires not just advanced designs, but also the industrial capacity to manufacture them properly. German superweapons that terrorized Allied populations through their impressive performance specifications were ultimately defeated by their own metallurgical limitations. The same steel that should have made them invincible instead made them vulnerable to failure at the worst possible moments. Dr. Margaret Whitley received her first glimpse of German metallurgical failures on June 6, 1944, when she placed that fragment of twisted steel under her microscope. What she discovered that day and in the months that followed revealed that Hitler's wonder weapons were indeed built to break, their impressive appearance masking fundamental flaws that doomed them to failure regardless of their revolutionary designs. The analysis proved that Nazi Germany's technological achievements were hollow victories, built on foundations of poor metallurgy, slave labor, and ideological interference with industrial processes. The Third Reich's pursuit of wonder weapons had created impressive prototypes that could not be manufactured reliably with available resources and expertise. That's how British materials scientists exposed the fatal weaknesses in German superweapons through metallurgical analysis that revealed systematic steel failures caused by Nazi policies that prioritized ideology over industrial competence, ultimately proving that Hitler's most advanced technologies were more dangerous to their operators than to Allied forces.